Hello. Thank you all for coming to my presentation. My name is Gabby Willis. I'm a PhD student at the University of Alabama, working under Shri Aleti at UA. I'm going to talk about some of the lessons we've learned from designing, fabricating, and testing some prestressed UHPC H piles. Before we start, I'd like to acknowledge and thank some of our sponsors. This project is primarily funded by Alabama DOT, but we have also received time and materials from SmartUp UHPC as well as Forterra in Birmingham. So a quick outline for the presentation. We'll begin by discussing the motivation as well as the objectives of this project, then go into section development and pile fabrication. We'll talk about material and experimental testing, and we'll finish up by talking about some of our preliminary conclusions as well as our next steps in the project, as it is still very much ongoing. So beginning with our motivation, the area of driven piles does have some concerns. So steel piles, although they have a high capacity, are easily damaged during the driving process, and they also corrode in their environment long term. In the top photo, we can see some corrosion in some steel piles in a bridge system. Prestressed concrete piles are a different alternative to steel piles, and those have a relatively good environmental resistance compared to steel piles, although, as we can see in this photo, we do still have some issues with that. But prestressed concrete piles also have a larger cross-section and a lot more weight, and they also damage during the driving process from the tensile stresses that those piles experience. And there's a photo of some of those driving tensile damage on the bottom there. So what's a possible solution? We want to create a durable and a drivable pile using an advanced material that can get the capacity of steel piles without seeing quite as much damage in the driving process. Ultra-high-performance concrete, or UHPC, as one of the previous presentations talked about, is a fairly new type of concrete that is characterized by its high strength, high pore flow, and good durability. Some of the components that make up UHPC include Portland cement, a lot of supplementary cementitious materials, lots of admixtures, specifically superplasticizers, and steel fibers, normally around 2% by volume on steel fibers. Because of these components, we can get compressive strengths up to 26 KSI. We can get sustained post-cracking tensile strengths ranging from 1.1 KSI to 1.7 KSI if we use that 2% by volume of steel fibers. And it is very durable. So as such, UHPC is pretty well suited to our task, which is to develop a UHPC H pile that is comparable to a steel H pile. So next we set out to develop our cross sections, but first we needed to create some goals and constraints on the project. So we chose to design two pile sizes, a 12-inch section that's comparable to an HP 12 by 53, and a 14-inch section that is comparable to an HP 14 by 89. These two steel pile sections are pretty common in ALDOT foundation projects. Two of our main goals were to keep the weight within 20 pounds per foot of their steel pile sections. And we also wanted to ensure that the constructability at the precast facility was fairly easy to maintain. We also wanted to keep some similar overall dimensions for these piles so that we could still drive them using existing pile caps. So some of the tools that we used, we took a lot of guidance from previous UHPC H pile projects, specifically Iowa State in 2008. My advisor worked on that project. We also used a lot of first principles analysis, as well as a lot of prior UHPC experience at the University of Alabama. So these are the sections we came up with. First, we have the UH 12 by 71, which has 8.6-inch strands, and overall the dimensions are 10 inches wide by 12 inches deep. And then we have the UH 14 by 105, which is overall 13 inches wide by 14 inches deep. One important note to make is that we did not provide any additional shear reinforcement in these sections. So this is what we're getting from these. Now, comparing our designed sections to their alternatives, we get an idea of where our piles fit. For both piles, we were able to stay within that 20 pound per foot goal that we set out. We also see a substantial increase in cross-sectional area, as well as expected load. For the 12-inch section, for the UH 12x71, we get a 54% increase in load compared to the HP 12x53, and we get a 32% increase for the UH 14x105 compared to the HP 14x89. With the sections finalized, pile fabrication began. We cast 13 total specimens with lengths ranging from 6.5 feet to 20 feet. And prior to casting, foil and embedded gauges were placed at several locations, specifically at the transfer length locations, as well as other critical locations depending on the specimen. For our flexural testing, most of those were around mid-span where we'd see the highest moments. These gauges were monitored both before and after pouring, as well as during detensioning, so that we could get an idea of what kind of short-term losses we're seeing in these piles. On pour day, the UHPC was mixed according to standard protocols. We checked the flow according to ASTM-C 1437. With the high flow rate of UHPC, the normal slump test isn't quite appropriate, so the flow table is used instead. We poured using an overhead bucket, as we can see in this top photo here. And we saw that the UHPC was able to flow through the webs around the strands, even when the webs were as narrow as 2.5 inches with that 0.6-inch strand in the center. So not a lot of room in there, but it worked out for us. Once all the piles were poured, we covered them to retain as much heat and moisture as we could. And they were allowed to cure largely in ambient temperature. Now, during the first 2 days when our strength gain was most critical before detensioning, we had some unexpected chilly nights in Alabama. So we placed propane heaters on each end of the bed to maintain a temperature of 75 degrees, but we didn't, of about 75 degrees, but we didn't apply any additional heat or anything. So we did notice some shrinkage cracks, voids, and what we call like a rough elephant skin on the UHPC after a day. You can see some of the larger voids that we saw, as well as some of the shrinkage cracks right there and right there. We suspect that this was because some of the piles were not immediately covered after pouring. We waited for all of the piles to be poured before we covered any of them. So some of the drying shrinkage could be for that, because of that. But after 2 days, we checked the strength. We needed at least 9 KSI of strength, and we got 13.9 KSI at that time. So we went ahead and detensioned. Now, regarding our short-term losses, we looked at all of our data from before the pour, the next day, and then during detensioning. Based on first principle calculations, we expected elastic shortening losses of 25 KSI, and we got elastic shortening losses of about 23.1 KSI. So we were very close on that. Those calculations matched pretty well to what we saw in the field. We also saw some higher shrinkage losses towards the top of the pile, which is less restrained than the bottom. And this graph shows just the times that we measured after pouring. So this first region was before we poured, where there's no strain in the system. And then 24 hours post-pour, where we are only getting shrinkage. And then the detention process, where we see a very swift drop or a swift increase in the compressive strains. And then once we got back from the field, we began our material study. For compressive strength, we tested 3x6 cylinders, which is standard for UHPC. We got a 1 day release strength, or we got a 1 day strength of 7 KSI, and then a release strength of 13.9 KSI. We reached 21 KSI by 21 days. And then after that, it's just been mostly plateauing since then. We tested more cylinders for the elastic modulus, where we got about 6,100 KSI at 3 days. And then tensile strength, we tested 8 direct tension specimens like this. They're 2-inch by 2-inch bars where we directly pull. And this is the stress strain curves for those tests, with the red being the average curve. We got an average strength of about 1.4 KSI. So all of these numbers were very much within our expected range based on our previous UHPC experience, both with this material and other UHPCs. And most recently, we've begun flexural testing. We started with the 12-inch pile in the weak axis bending direction. All of our flexural tests will use 4-point bending. For this one, we have an 11.5-foot span with 2-foot spaced load points. We calculated our expected failure before testing at 37.6 kips. So looking at our force displacement graph here, you can see that as we loaded and unloaded, we're pretty much coming back along the same curve over and over again. And we didn't really see any significant cracks occurring. However, we did observe micro cracking, which impossible to see. We had to rub acetone on the surface of the concrete in order to see that. And you can perhaps see that in this photo up here, circled in red. There are some very small hairline cracks while the load is still being applied. But along this force displacement curve, we start to see that we're deviating from our typical path around 30 kips. That's when we started hearing cracking noises. So that's when we started getting more damage occurring. We continued to load until failure, which occurred at 37.2 kips. It was a compression controlled failure. And then once we unloaded and reloaded, we still retained about half of that capacity. So we had some good residual strength in there. We instrumented the pile with a lot of different types of instrumentation. We used those previously mentioned strain gauges. We also applied some external strain gauges, string potentiometers, LVDTs, as well as a LED system that is non-contact and will measure the displacement while we test. And we took all of those instruments and all the data that we got from that, and we plotted the moment curvature 3 different ways and compared it to our theoretical moment curvature. That's this graph on the right over here. And you can see that they all agree pretty well. So our preliminary conclusions at this point, on the pile fabrication side, piles have to be covered immediately in order to minimize those drying shrinkage cracks and to avoid that elephant skin. We also found that the web thickness is often what's going to dictate our constructability because we have to make sure that we can get around the strands in the web in order to fill up the forms. To that point, using an overhead bucket isn't quite ideal because there isn't a lot of head height to push the UHPC into the forms. So not recommended, but it did work for us. We also found that our expected losses are really realistic compared to what we saw in the field. And then on the flexural testing side of things, we saw that if we use first principles analysis using the properties that we measure in the field, we can pretty accurately predict how these flexural tests are going to go. So our next steps in the project, because like I said, it's still very ongoing. We're still in the very early phases of full-scale or large-scale testing. We're going to continue the flexural testing in both strong and weak axis directions for both pile sizes. We're going to do shear capacity testing, again, both directions, with multiple pile sizes. We'll test a pile splice design, and then we will cast the piles into abutments, apply an axial load, and then we'll be able to get that combined behavior, which is very critical for pre-stressed H piles. But that is the end of my presentation. Thank you all for being here. And I guess if there's any questions, now's the time.